Hi, I'm Miram. I'm a first-year PhD here in the O'Reilly Group.
My name is Annika. I'm currently an undergrad student in my final year.
I'm Kes Jagdev and my supervisor is Dr. Richard Granger.
I'm Francie Alabush. I'm a postdoc in 2 research groups.
My name is Alessandro. I'm part of the iDesign PhD project.
I'm Kayla Delachai, a postdoc in the Dove group.
I'm Matt Wakeling. I'm a PhD researcher.
I'm Esme Williams, a master's student working in the Dove research group.
A part of my project involves polymer synthesis, and I use NMR to track the conversion of my polymers at certain time points during polymerization to ensure that they reach the target conversion. There are hydrophilic and hydrophobic parts in the polymers, and we change the hydrophobic parts. We use different hydrophobic monomers to investigate how they affect the final cloud point temperature of those copolymers.
My project this year was on electroorganic synthesis with sulfonamides. When you have normal organic redox chemistry, you use an oxidant or a reductant, which can usually be very hazardous. Whereas with electroorganic synthesis, the only reagents I'm putting into the system are my starting material and the electrons, so that then I can get my products with nearly no waste or just the side products. The walk-up NMR is very helpful because I can just come down with my sample, put my sample into the spectrometer, say whether I want a proton NMR, a carbon NMR, and then on the computer you can get the spectrum via email and you can later get the results of the server as well.
My project essentially focuses on making lots of selenium compounds as enzyme mimics. Selenium-77 NMR essentially allows me to look at what kind of environment my selenium atoms are inside of a molecule. So what are the substituents, more importantly what kind of oxidation state the selenium is in, and that is key information. You can't get this kind of information from, let's say, a standard hydrogen or carbon NMR. It won't tell you anything about how the selenium is sitting inside the molecule. Has it been oxidized to a silicon oxide? Does it exist as an anhydride? Or does it simply exist as a diselenide?
So my research entails making synthetic DNA probes for sensing applications for use in medical diagnostics. So NMR has helped me with my research in terms of making the small molecules which I put into synthetic DNA. For example, using fluorescent dyes to put into my DNA. They're small organic molecules, so I use NMR to determine the structure of them to make sure I've got the right molecule before putting them into DNA.
I'm part of the iDesign project. It's an EU-funded PhD project joined between the University of Birmingham and 2 industrial partners. As part of my project, I have to synthesize compound libraries of 3-dimensional molecules, and the good quality data that we get from these spectrometers with all the experiments that are already set up in the instrument, such as all the 2D techniques, HMBC, HSQC, COSY, we can easily elucidate the structure of the molecule.
In the Dove group, we focus on sustainable materials. Specifically, I'll be talking about our project on chemical recycling, where we can take commodity plastics like polyethylene terephthalate and bring them back down to their substituent monomers so that they can be repolymerized to a polymer with like-new properties. The reason we focus on chemical recycling is because at the moment, mechanical recycling often downgrades your polymers, so you can't use them for the same types of properties due to additives or contaminants from other plastic waste.
I'm working on the depolymerization project screening different acid and base catalyst combinations using the NMR machine to monitor the kinetics. I run the reactions in the lab. I take little samples every hour, make it into an NMR sample. I then use the NMR spectrometer to monitor the reactions. By comparing the different integrations of different peaks, I can see how much product's been formed, how quickly.
Our research group does a lot of synthesis and methodology work, so designing new methodologies to access new scaffolds. We utilise the spectroscopy facility a lot in our group to gain as much information as we can about the reactions that we're performing on a daily basis, and then we can take that information and purify our reactions with as little time in between the workup and the purification to obtain the best yields possible.